Good evening one and all. So in this video lecture I am going to discuss the construction procedure of root locus as well as effect of adding poles and zeros to open loop transfer function on the root locus. And in the earlier video lecture we have discussed about the basic fundamentals of root locus, where we discussed that a root locus is a plot of open loop control system's poles as gain reaches from 0 to infinity. Okay, and also we have discussed how the branches starts, where the branches starts from, as well as where they go. So we have discussed these things, and in this lecture let's see the rules which we use to construct the root locus. The first rule or first step, locate open loop poles and zeros in the S plane. Okay, so we'll be having open loop transfer function and we can calculate poles as well as zeros. Okay, so in the first step what we do is we just locate these poles and zeros on the S plane. The second one, find the number of root locus branches. See, in the previous video lecture we have discussed that the root locus branches start from open loop poles and end at open loop zeros. Okay, so the number of branches indirectly depends on the number of open loop poles or zeros. Okay, for instance, if the number of poles and number of zeros are equal, in that case they start from poles and end at zeros. But if the number of poles and number of zeros are not equal, then what happens? Then what is the total number of branches? In the earlier case where the number of zeros and number of poles are same, then the total number of branches will be the same number of poles or zeros. But when the number of poles and number of zeros are not equal, then whichever is high, that many root locus branches will be there. Okay, so here n is equal to p if p is greater than z, and n is equal to z if p is less than z. Okay, third step, identify and draw the real axis root locus branches. See, when we take S plane, there is a real axis as well as there is an imaginary axis. Root locus branches may be there on the real axis, or it may span anywhere over the S plane. Okay, so in this particular step what we are trying to do is we are trying to identify the branches which are lying on the real axis. Okay, so how we are doing this is we have one property, the phase angle property. So phase angle property says that if a point is on the root locus, then automatically the phase angle is odd multiples of 180 degrees. So this is what we have discussed. So odd multiples of 180 degrees means so let's directly take the point, then we can understand it when we take examples. Okay, so here what we do is on the real axis there may be some poles and zeros. Okay, in some cases there may not be. That time what happens is on the real axis there will be no root locus branch. Okay, for instance, if we have any poles or zeros on the real axis means imaginary part is 0. Okay, so if there are few poles or zeros on the real axis, then we will be verifying that, see that point, if odd number of open loop poles and zeros exist to the left side of a point, that point is any point, okay, on the real axis, then that point is on the root locus. Okay, so that means that after placing the poles and zeros on the real axis, we will be verifying whether there is any odd number of points towards left side of any point. Then we can come to know that there is the particular part of the real axis is the root locus branch. Okay, so we can understand it by taking example, and we will be taking an example in the next video. So the fourth step, find the centroid and angle of asymptotes. Okay, see, if p is equal to z, the root locus branches start at finite open loop poles and end at open loop zeros. That's what I said. But if P is greater than Z as well, or if P is less than Z, then if for instance if poles are more, okay, if poles are more, let's take poles as 4 and zeros as 3. Okay, we have 4 poles and 3 zeros. So how many branches will be there? There will be 4 branches in the root locus, because there are more number of poles, which is 4. So the total number of branches of the root locus is 4. Okay, now there will be 4 branches starting from these 4 poles. Okay, and 3 branches will end at 3 zeros. And what happens to the other branch? Okay, it should go to infinite. Okay, it should go to infinite. Similarly, when we have 3 poles and 4 zeros, we have 3 poles and 4 zeros, that time what should happen? 3 branches will start from these 3 poles and reach those zeros, 3 zeros, 3 of 4 zeros, there will be 4 zeros. So 3 zeros branches will come from these poles. Okay, but what about the other zero? The other zero will have a branch, okay, coming from the infinity. Okay, so here what we do is we are going to find out, see that point. So some of the root locus branches approach infinity when P is not equal to Z. The asymptotes give the direction these root locus branches, okay, the direction of these root locus branches. The insertion intersecting point of asymptotes on the real axis is centroid. Okay, so actually the poles are zeros if they are lying on the real axis. So a branch should come from the infinity, or a branch should go towards infinity. Okay, that time the angle of asymptotes is required. Okay, so we can calculate that angle of asymptotes using that particular formula, where theta is equal to 2q plus 1 into 180 degrees divided by P minus Z. Okay, and q ranges from 0 to P minus Z minus 1. So whatever the difference, so if we have only one branch that is coming from the infinity, or going towards the infinity, that time we need only one angle of asymptotes. That time we will be substituting q is equal to 0. Similarly, if there is another requirement, then we will be increasing this q. And the centroid alpha is equal to the sum of real parts of finite open loop poles minus the real part of sum of a real part of finite open loop zeros divided by the difference. Okay, so we use this centroid to find out the location where the branch is moving towards infinity from the real axis. Okay, so we will discuss these along with examples in the next video. Rule number 5: find the intersection point of root locus branch with an imaginary axis. See, the root locus branch, if it is crossing the imaginary axis, we should know where it exactly intersects the imaginary axis. So we are going to do that in this particular step. So we can calculate the point at which the root locus branch intersects the imaginary axis and the value of k at that point using the Routh method and a special case 2. So if all the elements of the Routh array are 0, then the root locus branch will intersect the imaginary axis and vice versa. Okay, so we have discussed Routh table. So in the second special case, where if we are getting all zeros, that time what happens is the poles exist on the imaginary axis with real part as 0. Okay, so that particular case will be used to identify this particular location where the root locus is intersecting the imaginary axis. Okay, so we will discuss this in the example. And rule number 6, find breakaway and break in. See, if there exists a real axis root branch between two open loop poles, yeah, see, let's take the example. We have the real axis and there are two poles, adjacent two poles are there. Okay, we know that root locus branch start from the poles. Okay, they start from the poles, and for instance, there are two poles and root locus branch is starting from those two poles, and both are in the opposite direction. If the branches are in the opposite direction, then what happens? So both the branches will touch those point and it will exit from the real axis. Yes or no? It will come out of the real axis from some point. That particular point we call it as breakaway point. And similarly, if two zeros are adjacent, then the root locus branch, it should reach to these zeros, and if the directions are exactly opposite, what happens is the two branches will meet the real axis at some point. Okay, that point we call it as break in point. Okay, and usually we calculate those values by you see that, follow these steps to find breakaway and break in points. Write k in terms of s from the characteristic equation. So 1 plus g of s into h of s equal to 0. Then differentiate k with respect to s and make it equal to 0, and substitute these values in s in the above equation, and the value of s for which k values are positive are called as breakpoints. Yeah, we will apply the same procedure in an example, and we calculate breakaway and break in points, and find the angle of departure and arrival. Okay, the angle of departure and angle of arrival can be calculated at complex conjugate open loop poles and complex conjugate open loop zeros respectively. Okay, the angle of departure and angle of arrival, the formulas are given, so we will discuss this with the example in the next video. So this is the process of construction of a root locus. Okay, basically it involves calculation of number of poles and zeros, and locating on the S-plane, and finding the centroid, and finding the angle of asymptotes, and then calculating that breakaway and break in, and finally the angle of departure and arrival. Okay, so this is about the construction of root locus and effect of adding open loop poles and zeros on the root locus. Okay, we have an open loop transfer function, and we, after plotting the root locus, if you add a single pole or a zero, what happens to the root locus? Okay, see, if we include a pole in the open loop transfer function, then the sum of the root locus branches will move towards right half of S plane. See, we are adding a pole in the open loop transfer function. Okay, because we are adding a pole, so what happens, one branch will be added, as well as that branch is from that part, that branch is starting from that pole. Okay, and it will go towards infinity in general, and if there is a branch coming from the infinity, that particular branch will now come from this particular pole. Okay, so when a pole is added, the root locus branches will move towards right half. Okay, see, when the root locus is moving towards the right half, then automatically what happens, the stability will reduce. Okay, there is a chance of becoming unstable, because if the pole previously located in the left side now may move towards right. Okay, so that's why, so there is the stability tends to reduce. Okay, and damping ratio decreases, which implies damping frequency increases, and time domain specifications will decrease. Okay, and on the other hand, if we include a 0, the reverse will happen. Okay, the root locus will shift towards left. Okay, that time what happened, the stability tends to increase, time domain specifications will increase, and damping ratio increases, and damping frequency decreases. Okay, and whether we are adding a 0 or pole, it all depends on the application. Okay, thank you.